This is geometry lesson 12.4, the fundamental theorem of similarity. So our big idea says in similar figures that are not congruent, ratios of corresponding lengths, areas, and volumes are all determined by the ratio of similitude, but they are not equal to each other. Okay, so the general theorem that we're going to look at today says this: if two figures are similar with a ratio of similitude k, remember that's the same as scale factor, that's the proportion that the sides are going to be in. It's what you're multiplying to get from one to the other. Then we always know that corresponding angle measures are equal. The angles don't change when we enlarge or shrink something. Corresponding lengths and perimeters are in the ratio of k. That's what we've been studying. So all of the side lengths will have the same factor. So if they all increase by 5 times or half or 2 times, that's going to be true for all the lengths of the sides. They'll all be with the same factor of k, whatever it is. And because all the sides are changing by the same proportion or the same factor, the perimeters will as well. But one of the most common misconceptions with students is that if we triple all the side lengths, that the area is also tripled. Or if we multiply all the sides by 10, the volume will also multiply by 10. And that is not true. Okay, so number 3, the corresponding areas and surface areas will be in a ratio of k squared. So if all the side lengths had been multiplied by 5, right, the perimeter will also increase by 5 times, but the area will increase by 5 squared times, so actually 25 times. And volume is going to increase with the ratio of k to the third power. So if all the sides of a three-dimensional shape are multiplied by 5, the volume is going to increase by 5 to the third power, so by a lot. So not just 5 times, but a lot more. And that's because each individual length, like base, height, width, all that stuff, they're all being increased by 5 times, and then they're all going to get multiplied together. So 3 different things are changing for volume. Remember that the units for volume are always to the third power because we multiplied inches times inches times inches. Well, if each one of those units was increased by a factor of 5, that's why it's not just 5 times bigger, it's 5 times 5 times 5 times bigger. All right, so that's easy to remember, but also down the road, easy to forget. So let's take a look at some examples to prove this to be true. And I think when you actually see it done, it helps memorize those things. Once we know that area, which is area of a two-dimensional shape, or surface area of a three-dimensional shape, is squared, just like the units, we're used to that, and the volumes are to the third power, just like the units that we're used to. It is pretty straightforward, but I think seeing it will help us remember. So for example, number 1, we've got two basic two-dimensional shapes. Create the image of each shape after a size transformation of 5, and then find the new area. So we're going to draw a bigger triangle. Don't have enough space to truly make it 5 times bigger, but we're going to go ahead and make the lengths bigger. So we're going to do 6.8 times 5, which is 34. And we're going to do 10 times 5, which is 50. All right, so we have undergone a size transformation. S looks like a 5, so it's not great, but size transformation of 5. And what we're going to do is we're going to examine the two areas. So the original area, remember a triangle is 1/2 base times height. If we run those numbers, the base is 10, the height is 6.8. You run those all the way through. So we're going to do 0.5 times 10 times 6.8, and we get 34. And now this is meters squared. And according to this won't increase by 5 times, it will increase by 5 squared times. So if I took 5 squared, that's 25. So the area should now be 25 times bigger, not just 5 times bigger. The side lengths, all of the corresponding pieces besides the angles, will all be 5 times bigger. 10 became 50, this became 34, but the area will increase by 5 squared. So 34 times 5 squared, or 25, is 850. So we're predicting that the area of this is going to be 850. So let's take a look. Same formula, 1/2 base times height. The base now is 50. The height is 34. 0.5 times 50 times 34. And there is our 850. So again, the most common misconception is that if I increase all of the sides, if I enlarge this by a factor of 5, the area will also increase by a factor of 5. So people, if they knew that the area was 34, they would times it by 5 and they say, oh, the new area must be 170. But in fact, it's 5 squared because these are going to get multiplied times each other. We times this by 5 and this by 5. So two things, we'll square it. And so it's actually 850. So let's look at the same thing with the circle. If we perform a size transformation of 5 on the circle, again, not enough space to physically make it 5 times bigger, but we will change the dimensions here. 3 times 5, now the radius is 15. The old diameter would have been 6. The new diameter is 30 times 5, right? 5 times bigger. So the original area here, pi r squared, 3 squared, 3 squared is 9. So the original area was 9 pi. And so if we go ahead and we increase and perform a size transformation of 5, some people would just times this by 5 and say, oh, the new area must be 45 pi. But according to this new theorem that we're looking at here, it's going to increase not by 5 times, but by 25 times, 5 squared. So if we go ahead and do 25 times 9, that's 225 pi. And so we're going to go ahead and assume that's what's going to happen here. And let's run the numbers and show that that's actually what happens. Pi times, now the radius is 15. 15 squared is 225. So 225 pi. Now students a lot of times see over here, okay, we changed this by 5 and this by 5, two different dimensions. So then it makes sense that this increases by 5 squared because we changed 5 here and 5 here, 5 twice, 5 squared makes sense. But what about over here? We only changed one dimension, right, the radius. But that radius in this formula gets squared times by itself. So the 3 was actually 3 times 3, and then it became 15 times 15. So actually two different units because the radius was times itself. Two different things were increased by a factor of 5, so that's why the total area increases by 5 squared. All right, let's look at what happens with volume. To go back to our theorem here, the corresponding volumes will be in a ratio of k to the third power because we're multiplying three things together to create volume. So we're going to look at both surface area and volume for these. So we're going to have a size transformation of 3. So I'm going to draw this shape. I'm definitely not going to try and make it bigger. I'm just going to try and draw it. Not the easiest shape to draw. Not bad. Okay, so we are timesing this by 3, size transformation of 3. So the bottom, 7 becomes 21, 7 times 3. 8 becomes 24, and then the height, 3 times 3 is 9. So those are your new dimensions, 21 by 24 by 9, and you could spread those out throughout the picture. So let's start with surface area. Surface area is going to follow your area ratio, so it should be just like these. Whatever the ratio of similitude is squared, that's going to be the ratio of the surface areas, and then the volumes will be to the third power. So let's keep those straight. So surface area of this type of shape is the lateral area, perimeter times height, plus 2 times the area of one of the bases. So with the original shape, let's go ahead and plug that in. Perimeter would have been 8 plus 8 plus 7 plus 7. We'll call this bottom part the base. Add up all the way around. That is 30. The height, the distance between the bases, is 3. And then the area of the base is just 8 times 7, and there's 2 of those. 8 times 7 is 56. So this is 90 plus 112. So the surface area of my original is 202. And if we're going to do units, that's meters squared. All right, so according to our model, this is going to increase by the scale factor squared. So instead of just times 3, the surface area should actually increase by 9 times, 3 squared, 9 times. So we're going to do 202 times 9, and we're going to get that big number, 1,818. So the new surface area of our shape that underwent a size transformation of 3 should be 9 times the size of the original, 1,818. Let's go ahead and run it and make sure that's actually what happens here. So again, surface area is perimeter times height plus 2 times area of the base. Our new perimeter here, 21 plus 21 plus 24 plus 24 is 90 times the height of 9. And then 2 times the area of the base, that's 21 times 24, which is 504. So this is going to be 2 times 504, which is 1,008. 90 times 9 is 810. And if we add 810 plus 1,008, sure enough, there is our 1818. So surface area equals 1818. So the original surface area was 202. Size transformation of 3, all of the sides have been multiplied by 3. The surface area increases by 9 times, which comes from 3 squared. Now let's look at volume. Volume's easier to calculate. So the original shape, volume is big B times H. Well, big B is just the base times the height of the base, so 7 times 8 times the height of 3. 56 times 3. I've got that number here is 168. And remember, this is to the third power. We multiplied meters times meters times meters. It's meters to the third. So according to our theorem up here, this will increase by our scale factor to the third power. So 3 to the third power. That's how many times bigger the volume should be. 3 to the third is 27. So it should be 27 times bigger. 168 times 27. And you could always do 168 times 3 raised to the third. Same answer. We should get 4536. 4536. So let's try it. Our new larger shape, still big B times H. Area of the base is 21 times 24 times the height of 9. 21 times 24 is 504 times 9 is 4536 meters to the third power. So sure enough, the original volume was 168. We increased all the sides by a factor of 3, and now the volume is 27 times bigger. And so we're doing all of this to prove it, but in the future, if we know that this area volume is 168 and there's been an increase with the scale factor of 3, we can just multiply this by 27 and say, hey, the new volume is going to be this. We actually don't have to run the formula. So we're proving this is true so that in the future we don't actually have to do all this work. All right, so one more of these. Find the new surface area and the volume, again, after a transformation of 3. So we're going to have a bigger cylinder here, 3 times bigger. All the dimensions are 3 times bigger. So if this was 4, 4 times 3, the radius is now 12. And the height was 10 times 3 now. It's going to be 30. So we're going to do surface area again and volume to prove this. Surface area is perimeter times height, but perimeter, remember, is circumference of a circle. So pi times diameter times the height plus 2 times the area of the base, which since it's a circle is 2 pi r squared. So let's plug everything in. Original shape here, the diameter all the way across is 8 times the height of 10 plus 2 times pi r squared is 4 squared. So right here, 8 times 10, we have 80 pi. 14 squared is 32 times 2. I'm sorry, 14 squared is 16 times 2 is 32 pi. And we're going to go ahead and put those together. That's 112 pi. So knowing that, we can already figure out what this is, right? We increased it by a factor of 3. The area or the surface area will increase by that factor squared. So 3 squared or 9. It should be 9 times bigger. So 112 times 9. We should get 1008 pi. So let's run it and make sure that's what happens. So pi times diameter, that would be 24, times the new height of 30, plus 2 times pi r squared, 12 squared. So 24 times 30 is 720, so 720 pi, plus 12 squared, which is 144, times 2, because there's 2 bases, is 288 pi. And if we do 720 plus 288, sure enough, the new surface area is 1008 pi, just like we predicted. So again, increased by a factor of 3, the surface area increases by a factor of 3 squared or 9. It's 9 times bigger. And the volume then should be 27 times larger. Let's prove it. Volume much easier to do. Volume equals big B times H. Big B would be pi r squared times H. So we have 4 squared here. And that's going to get times by the height of 10. This is 16 pi times 10. So volume equals 160 pi. So 160 times 3 to the third power for volume, you should see an increase times 3 to the third of 27 times bigger, which is 4320 pi. Quick check over here. Volume equals big B times H, pi r squared times H. So pi times 12 squared, radius is 12, times the height of 30. So 12 squared times 30. Sure enough, volume is 4,320 pi, 27 times bigger. All right, so we've proven this to be true now. The side lengths have all changed and been 3 times larger, which makes the surface area or the individual areas of the faces 9 times larger, 3 squared, and then the volume is 27 times larger, 3 to the third power. So we've proven this to be true now, and so now we no longer have to go through and show all of this. We can just use those facts to help us solve a problem. So that's what we're going to do real quick on the back. These will be quick and easy now that we've proven this all to be true. All right, so here at the right, PINK, the smaller one, is similar to ROSE, so this is just an enlargement. Pink has an area of 20 square units. So the area is 20. What's the area of rose? So this is an odd shape anyway, right? We don't have a formula to go ahead and figure out what's the area of this shape. But because we can see these side lengths are in a proportion of 5 to 11, we can figure out what the 5 was multiplied by to create the 11. And then we can apply that same scale factor or ratio of similitude to the area, but it will be squared. So first of all, our scale factor, you always go from the second one or the image back to the pre-image when you compare these. So it's 11 to 5. We could leave it like that, or we can go ahead and divide 11 by 5. It's not a bad number. So it's 2.2. Okay, so it's increasing by a factor of 2.2. You multiply 5 times 2.2, and you get 11. So all of the side lengths would be multiplied by 2.2. We don't have anything else. So the ratio of the area, okay, the original one was 20. It's not going to increase by 2.2. It's going to be 2.2 squared. Area, like we studied on the front, is always going to be in a ratio of whatever the ratio of similitude is, or scale factor is, squared. So ours is 2.2. So this is going to get multiplied by 2.2 squared. So 20 times 2.2 squared. And we get 96.8. So the new area over here is not 2.2 times bigger. It's 2.2 squared times bigger, which is 4.84. I do want you to see this with a fraction as well. So we could have left this as 11 over 5. We would have done 20 times 11 over 5 squared. You could plug that all in your calculator, but let's make sure we know what this actually does in terms of the algebra. The 11 gets squared. 11 times 11 is 121. The 5 gets squared. That's 25. So this is actually the factor that we're multiplying by. The 11 compared to 5 squared. So you could do this in your calculator. 20 times, use your fraction key, 11 over 5 squared. Now notice it gives you a fraction. So let's say you get that fraction. We don't want to leave our answer like that, so you do 484 divided by 5. And sure enough, there's our same answer of 96.8. So this was 484 over 5, which when we divide is 96.8. And down here, we could have done the same thing. So 20 times. Now, instead of using the fraction key, I'm just going to go ahead and write this as 121 divided by 25. And then it'll give me a decimal answer instead of a fraction. And again, it's 96.8. So I just threw a lot at you to show you different ways of doing it. But in general, this is very simple. They gave you the area. First, you got to figure out the scale factor. Set them up as a ratio of the second one to the first one, 11 over 5. Leave it as a fraction, turn it to a decimal. If you turn it to a decimal, it can't be a crazy decimal. It's got to be a nice one. If you get a crazy decimal, leave it as a fraction. And now the area is going to increase by that factor squared. And volume would increase by that factor to the third power if we were talking three-dimensional shapes. All right, so one more quick example here. So we have two scale models of cars. This looks like a full-size car, but these are both miniature toy cars, scale models. Scales meaning everything's in the correct proportion to the actual cars. So that's what they say. Every model is similar to the actual car, which means they're also similar to each other. The smaller model is 15 centimeters in length, while the larger model is 75 centimeters in length. So this little one is 15, and this bigger one is 75. It doesn't even matter that we get that on the right spot here. We just know that that's going to be the ratio between the two. So how do the heights of the models compare? So the heights are just a single length. Here you got length, height, width. We already know one comparison is 75 to 15. So the heights are going to also be in that same ratio. So if I compare 75 to 15, and you could do it the other way. Now I'm going to put the larger number on top, and it's going to show what it's increasing by if I go this way. But you could absolutely do it the other way as well and show that this one is shrinking to create this one. If you divide 75 by 15, you're going to get 5. So how do the heights compare? 5 times the size. If you had gone the other way, you would have got 1/5, and you'd say this one is 1/5 of the size. And that's true. It's a little easier to just think about it as an enlargement, though, with 5 times the size. This is your scale factor. All of the dimensions of the smaller one are being multiplied by size transformation of 5. So with that information, if I found the whole surface area of this model compared to this model, how many times bigger is the surface area of this one compared to this one? Well, the dimensions are all 5 times the size. Area is always squared. So it's going to be 5, which is our scale factor, squared. Let's jump ahead before we solve that. How do the volumes compare? You take your scale factor of 5, and it's going to affect the volume as 5 to the third power. So 5 squared we know is 25. So how do the surface area of the models compare? 25 times the size, So the bigger model is going to have a surface area 25 times the size. And the volume, how much fits on the inside of this, 5 to the third power, or 5 times 5 times 5, is 125. So the volume, when I increase all of the side lengths, all of the dimensions by 5, the volume increases by 125 times the size.